Okay, so now that you know where the electrons are, what kind of electrons each atom has, I want to talk about valence electrons. Now, valence electrons are going to be really important when we start looking at how compounds are formed, how elements go together, what proportion the elements are going together to form the compounds. So, the definition for a valence electron is this. It's the number of electrons in the highest principal energy level. It's supposed to be an S there. Looks weird. Principal energy level. So, it's going to work like this. All right? Let's say I have an electron configuration of sodium in A. I'd go 1s2, 2s2, 2p6, 3s1. So I look for the highest principal energy level. In this case, it's the third. The number of electrons is designated right there. So my number of valence electrons would be equal to 1. All right? So let me do another one. This one might be a little trickier. I'll do... okay, let me completely... Okay, there we go. So this time I'm going to pick... let's pick something like vanadium. All right? So I'll do the long vanadium, but it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, then 3d1, 2, 3. Now, according to the definition, highest principal energy levels, I look at the highest principal energy level is 4. The number of electrons in that level is 2, so vanadium has 2 valence electrons. All right? So D's end up not counting. D electrons don't count in terms of valence electrons. All right? So now I want to just show you a real easy way to do it so you can do it quickly. This is the official way, but here's the quick way of doing it. Go into a periodic table. All right? Anybody in the first row of the periodic table right here will have 1 valence electron. Anybody in the second row is going to have 2 valence electrons. Anybody in this row will have 3 valence electrons, then 4, 5, 6, 7, and the last noble gases will have 8. So it's very simple. So you can just look up the periodic table and let's go to strontium right there. And if I asked you how many valence electrons there's going to be in strontium, you'd say 2. If I go over and pick, let's say I pick bromine right here, how many valence electrons? You'd say 7. Now you could show that in the dot diagram, everything else. For example, with bromine, the long bromine is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. There's a 10 there. It doesn't really look like a 10. And we could do a better job. Uh-oh. So, anyway, I erase the PDF when I do that. Anyway, that's 3d10 sitting on top of there. And then 4p, 1, 2, 3, 4, 5. All right? So, highest principal energy level is level 4. I add the 2 with the 5, and I end up with 7 valence electrons. All right? Now, one thing you maybe notice is these elements, all right in here, the transition elements, they are all going to have 2 valence electrons. And the reason for that is you're always stepping back. I'd be at 4s2 right here, but then I drop back to the 3d. 3d is a lower principal energy level and they don't count. So since the transitions always fill up d's at one lower principal energy level, they're not going to count. So to get this right, alkali metals, right here, 1 valence electron. Alkaline earths, right there, 2 valence electrons. All of the transition metals, 2 valence electrons. Anybody in this column going down has 3, then 4, 5, 6 for the oxygen family going there, 7 for the halogens, and then finally 8 for the noble gases. Actually, that doesn't include hydrogen. Okay, hydrogen has 2 valence electrons. Not hydrogen, oops, sorry. Helium, right there, has 2 valence electrons. So don't mess that up. That's kind of an exception. 2 valence electrons, because it doesn't have p's. Alright? Okay.